Yeah, good morning. I'm going to give you a primer on permutation tests, not only for MVPA. Something I think it's important to realize is that the principles of permutation testing apply in a uniform way in uni and multivariate analyses, and that's actually a strength. What did I do it? Okay. So, why use a permutation test? Most importantly, because sometimes precise distributions are not known. This is especially the case in MVPA. Precise distributions are not known. That applies on different levels. Sometimes we don't want to make strong assumptions about the distribution of the data. Standard assumption would be something like normally distributed, the GLM assumptions. The other thing is, even if we were ready to make distributional assumptions regarding the data, that doesn't mean that we can compute the distribution of test statistics, especially in MVPA, something like the distribution of cross-validated classification accuracies. So a permutation test makes weaker assumptions about the data, about the distributions and parametric tests. Also, that is important to realize. It's weaker assumptions. It's not that there are no assumptions. So you still have to be careful that the assumptions of the particular test that you're applying, the specific exchanges that you're doing, are actually warranted. So you have a reasonable null hypothesis. Another advantage is that permutation tests provide exact inference. Exact inference means if you design a test to have an error rate, a false positive rate of 5%, and the assumptions of the weak assumptions of the test are given, then you actually get a test that is at a level of 5% and not something else. And yeah, I said this before, permutation testing applies in the same way, in the same logic to uni and multivariate analysis, which is why I will explain both together. In this talk, I'm not going to give any particular recipes for specific situations. There are so many different situations you might encounter, but I'm going to try to explain to you the basic principles underlying permutation tests, in particular the principle of exchangeability, so that you can use this knowledge in order to design your own tests or to check whether tests performed by other people are actually valid. I'm starting with a simple example, univariate example, the two-sample test. So the situation in which you would normally, in a parametric setting, you might employ a two-sample t-test. We have data from two groups, let's say groups of people, A and B. We have three samples in each group, 714 and 639. And the question is whether the distributions these data points come from have a difference in mean. What you do is you start from the original data and you compute a test statistic. So choosing the test statistic, there may be some advantages or disadvantages regarding a particular permutation setting, but generally the test statistics and the permutation scheme are two different things. The permutation scheme has to be valid or has to be attuned to your null hypothesis. What are you willing to assume under the null hypothesis? The test statistic you can choose relatively freely, even though in some cases there might be some optimizations you can perform if for a specific combination of a particular permutation setting and a specific test statistic. So here we're interested in a mean difference. So naturally what we could do is we compute the sample mean for the two groups. Sample mean for group A is 4, sample mean for group B is 6. Difference between them, x bar B minus x bar A is 2. So value of our test statistic is 2. Now, under the null hypothesis, if we assume there is no mean difference between this distribution, the distributions these two samples come from, and if we are also willing to assume that actually not only the means are the same, but the distributions themselves are the same. So basically, every value in group A could just as well have arisen if in sampling in group B and vice versa. That means we can exchange values between these two groups. So for instance, we could exchange the values 7 and 6 between groups A and B, or we could exchange the values 1 and 9 between group A and B. If we perform these exchanges, we get permuted data. So now in group A we have 694, in group B 731. Now we do exactly the same as before, computation of the test statistic, mean per group and difference of the group means. And now the permutation test statistic is minus 2.67. The procedure for a permutation test, at least in principle, is to do this for all possible permutations. So another thing that I think is important to realize, permutation tests in themselves, out of principle, there's nothing random about them. The data are random, but the permutations arise from properties of the null distribution that you are willing to assume, and for a certain number of, for a certain set of assumptions, there is a certain set of permutations, and if you want to do it perfectly, you would have to use all the permutations that there are. Luckily, in this case, we have two samples with three values each. There are only 20 different permutations. Note that the first permutation is actually the original data. So there's always a neutral permutation which doesn't change the data, and for convenience, it makes sense to give this permutation the index number 1. So in the first line, we have permutation number 1, the original data, 704, 639, test statistic 2, and then we have all the possible permutations with their respective test statistic values. Then we determine the ranks of these values by sorting them, in this case sorting in descending order, indicated by the arrows. So the largest value in these permutation values is 4.67, the second largest is 3.33, and so on. And also the original value of the test statistic 2 arising from the neutral permutation has a position in this. It's the rank number 5. Now we can decide about significance of this value, this test statistic value 2, in two equivalent ways. We can either say we want to have a test at a level of 5%. We have 20 permutations, which means 1 out of 20. So we can simply say it's significant if the actual value of the test statistic is the largest one and has a rank 1 in the permutation set. Or we can compute the rank, or we can use the rank of the neutral permutation value 5 and transform this into a p-value. P equals 5 over 20, which is 0.25. So this would be our p-value, and we can compare it to the level we are interested in, let's say 0.05, and we see it's not significant. This was a test for an increase, mean in the group B larger than in group A. If we want to do the in reverse, we just use the inverse, or the negative test statistics, x bar A minus x bar B. Everything, the whole order is reversed. Now, the original value of the test statistic is -2, and it turns out in the ranking that it has a rank 16, corresponding to a p-value of 16 over 20, or 0.8. Again, not significant. And we can also do a two-sided test, which means we use a test statistic, the absolute value of the difference of the means, and this time the test statistic value is again 2, and it turns out to have a rank of 10. I'm saying 10, in this case it's a little bit more complicated because there is a tie. There's another permutation, which is permutation number 20, which has the same test statistic value, 2. And I have given it this other permutation, the rank 9, and the neutral permutation, the rank 10. If you want to be on the safe side, this is the thing to do. If there are ties, always give your original permutation, your original test statistic value the highest possible rank. At the expense that the test is a little bit conservative, so it's probably also a little bit less powerful than it could be. An alternative would be to choose randomly. So you could flip a coin and say, if it's heads, I take the rank 9. If it's tails, I take the rank 10. So we would get with 50% probability either a p-value of 9 over 20 or a p-value of 10 over 20 or 0.5. Summary of the formal procedure for a permutation test. What you have given is a data set. You decide upon a test statistic. The test statistic does not come out of the permutation test. You set a significance level, alpha, and most importantly and probably most challenging in many cases is you have to decide on the possible exchanges that you can apply to the data. You compute the test statistic for the original data. I think it's convenient to give the permutations, the neutral permutations, the index 1. So T1 is a value of the test statistic on the original data. Then you compute the test statistic for all permutations. I equals 2 to NP, where NP is the number of permutations. I equals 1, as I said, is a neutral permutation. Or if there are very many permutations, you can't compute them all. You don't have the computing power to do that. You can also do a random selection of values. This is a test that on average will also be exact, but still you have to include the neutral permutation value T1 in the set. So 2 to NP will be the ones that are randomly selected. You then determine the rank of the original value of the test statistic in the set. The easiest way to do this is via this formula. The rank R is the sum over I equals 1 to NP of Ti larger than or equal to T1. These brackets indicate that if the condition in the bracket is true, it has a value of 1. If the condition is wrong, it has a value of 0. Or to put differently, the rank is just simply the number of values, permutation values, which are as large as or larger than the original value of the permutation statistic, of the test statistic. And then you convert this into a p-value. P equals rank over the number of permutations, R over NP. And you decide upon rejecting the null hypothesis by comparing to your your set significance level alpha. If p is smaller than or equal to alpha, then you reject the null hypothesis. This test is exact if your significance level alpha is an integer multiple of 1 over np. So if you do some random selection, you should look out that you pick the correct or a compatible number of permutations in order to exactly achieve your significance level, and under the condition that there are no ties. So if you have many different permutations with the same value of the test statistic, then according to this recipe, you will get a conservative test. As I said, alternatively, you can pick ranks randomly out between ties. Now, the important principle underlying this is the principle of exchangeability. And the simplest case of exchangeability is independent and identically distributed. If you have independent samples which come from the same distribution, and then what you see in this plot, we have two different variables, x1, x2. They are these two different distributions. The color coding is the joint probability density function of these two variables, and we're assuming that they have the same distribution. In this case, it's simply a normal distribution around 0 in both cases, and they are independent. This is why the joint distribution is spherical, so it has these rotation symmetric structure. If we now exchange x1 and x2, this means that we flip this joint distribution over the diagonal, indicated by this gray arrow. So x1 becomes x2, x2 becomes x1. And we look at the resulting joint distribution, we find that it looks exactly the same. That is exactly the principle of exchangeability. Two values are exchangeable if under their exchange, their joint distribution does not change, it is invariant. Of course, this is a simplified picture because we only have two different values, so you cannot really visualize this for more complicated situations. But the general rule is if you have a certain number of values, and you consider your null hypothesis, if you exchange any two of them, the joint distribution of all the values has to stay constant. That is the condition of exchangeability. And as I said, the simplest case in which this is given is IID, independent identically distributed. Now, if these two values came from different distributions, for instance, x1 had a mean of 0, x2 had a mean of 1, and we would apply the same exchange of x1 and x2, of course, the joint distribution would change. The center of the distribution is now somewhere else, which means in this condition we do not have exchangeability. And that is exactly the logic of the null hypothesis test. Under the null hypothesis, you have exchangeability. Under the alternative, you do not have exchangeability. Exchangeability goes beyond IID, independent and identically distributed, because there can also be dependency. In this case, we have a symmetric dependency between these two. This is, again, a normal distribution with some correlation. And now both the marginal distributions are the same. Both distributions have a mean of 0. There's a positive correlation between them. So we have this elongated shape of the probability density function, the joint probability density function. If we apply the flip, you can see, again, there's no change. So we do have still exchangeability even if the values are not independent. That's an important feature of permutation tests that is hard to emulate in parametric tests. Most parametric tests depend on the assumption of IID. Permutation tests also work in other settings, like this setting where you have this symmetric kind of correlation or dependency between different variables. And again, if the mean of one of the two distributions is different, you do the flipping, you get another joint distribution, so there's no exchangeability. So exchangeability allows you to distinguish between your null hypothesis and the alternative. Okay, back to the example. Univariate two-sample situation. We have independent values sampled from two univariate distributions. Our null hypothesis says that the two samples come from the same distribution. This is the IID case I explained before, which means that all the values can be exchanged freely, as indicated by the blue arrows between these circles. You can exchange every value in group A with every other value in group B. What you do is you generate the permutations that come out of these exchanges. For each permutation, you compute the difference of sample means and use this as a test statistic. And what you get is a permutation analog of the two-sample t-test. In fact, the results will often be very similar to the parametric test. Now, multivariate, finally multivariate. We assume that we now have multivariate values. We have vector values indicated by these small arrays. But we still assume that they're independent sampled from two multivariate distributions, and our null hypothesis is that the two samples come from the same multivariate distribution. Again, we have the IID case. Again, we can exchange freely, but what we are exchanging now are vector values. We never just exchange one component of one vector with another component of another vector, but we exchange whole vectors because this is exchangeability given by our null hypothesis. Again, we have, in this case, two samples with three values each. We have 20 different permutations. What we now do is we compute a different test statistic. And there are many possibilities what we can do, but something that would be popular in MVPA, would be standard choice in MVPA, is that we train and test a classifier in a cross-validated version, and we get, as a test statistic, the cross-validated classification accuracy. So we can apply exactly the same scheme as before. We have 20 different permutations, it's correspondingly 20 different accuracy values. So we compare the actual accuracy with the distribution of accuracy values and get a p-value and therefore make a test. One problem with accuracies is that, especially in a case like this one illustrated here, if we have a few number of data points, that accuracies have few possible values. Basically, accuracies are counts. So if you have only 10 different values, you can only get 10 different accuracy values, which means you very often will get ties, which means you have this problem in the ranking of the permutation values that you have to somehow solve. One possibility, as I said, is randomization. If you do this in spatially extended way, for instance, searchlight analysis of fMRI data, you can apply a little bit of smoothing, which will break the ties. You have to think about what is the right way to break ties in your specific situation. Otherwise, you will get very conservative tests. So now there's a multivariate example with IID. This could, for instance, be concern the classification of subject-specific patterns. So you have subjects that fall into two different groups, A and B, and you have some, let's say, structural features of their brain, and you apply the classification there. For instance, patients where you want to classify, you would distinguish between normal controls and people with a pathology based on their structural MRI. Next standard situation is the univariate paired test, analog to the paired t-test. Now we don't have IID, but we have paired values. So we have, again, two groups of three values, but for each value in group A, there's a corresponding value in group B, and they are somehow related. For instance, they come from the same subject, or they are extracted from the same data set. So we can assume that there's a correlation, a statistical dependency between them, which is indicated by these black lines connecting them. So the first one of A is connected to the first one of B, and so on. Now we have partial dependency, but this doesn't stop us from making permutations. We can exchange within pairs. We exchange the first value in group A with the first value in group B, or the second value in group A with the second value in group B, and so on. In this case, of course, there are very few permutations that are possible, 2 to the n, so 2 to the 3, 8 different permutations in this case. Hopefully, in real situations, you will have more values, so therefore more possible permutations. Then, following this, the logic is actually the same. You can compute the difference of sample means, x bar b minus x bar a. because you have a test statistic that is sensitive to difference in means, this is a permutation analog of the paired t-test. And of course, we can do exactly the same in the multivariate case. We have now multivariate correlated values, let's say pattern vectors extracted from the fMRI of a subject in two different conditions. Because they are extracted from the same correlated fMRI data, they will be correlated. So the pattern vector from subject 1 will be correlated to the pattern vector in condition B from subject 1, but you can still do these pairwise exchanges. And then, of course, you can do something like train and test a classifier, cross-validate it, get an accuracy, and apply a permutation test. Example for this would be the classification of condition-specific patterns in fMRI across subjects, or it would be the classification of patterns across runs within subjects. So for MVPA, also for the purposes of cross-validation, you would like to have independent subsets of the data, so you might make, let's say in this example, 3 different recording sessions. You extract pattern vectors for 2 different conditions from each run separately. Then you can be reasonably sure that the pattern vectors from different runs are independent, but they will certainly be correlated within runs, so this would be an appropriate permutation scheme in this case. Basically, I've already mentioned this. There is a problem for exchangeability in fMRI time series. fMRI trials occur in a time series, and we know that fMRI exhibits serial dependency. So let's say we have a very simple design with trials of 2 different classes, A, B, B, A. So there's a randomized sequence of trial types. And as the horizontal lines connecting the bullets indicate, there is a serial dependency. If you have the value obtained from the first trial in condition A, and you have another value obtained from condition B in the second trial, you know, or you must at least be prepared to acknowledge that there is a correlation between them. Now, if we were to exchange values between groups of trials of different conditions, for instance, would exchange the 2 different, the 2 middle trials, you get another correlation structure as indicated above. You suddenly wouldn't have a correlation between the second and the third trial anymore, between the second and the fourth trial. And the fourth would be correlated to the third, but the third would be correlated to the fifth. So you have a different correlation structure. So this is the reason why you cannot simply exchange measurements from different trials out of a continuous time series in fMRI. You change the correlation structure. And even though permutation tests can deal with certain cases of correlations, with certain cases of dependency structures, in this case, we don't have this global symmetry that would be needed in order to exchange any 2 trials. No exchangeability of values in fMRI time series. There is another approach, which is not a permutation test, even though it is very frequently confused with a permutation test. The procedure is very simple, but the rationale is completely different. If, as I said, the trial sequence, the sequence of conditions in this time series has been randomized, it has been chosen randomly, then you can use this as a basis to exchange labels, not data points. You know that B and A could have been A and B in a different randomization of the design, so you can exchange this. This rationalization leads to the so-called randomization test. As I said, it's not a permutation test because it's not about exchangeability of data, but it's about exchangeability of labels. We randomize the labels, therefore we have exchangeability in the labels. We do not have exchangeability in the data. But there's a disadvantage to this. Randomization tests are exact only on average across different designs. In some cases, it might not be so bad. Maybe you have a long sequence of trials, and if you re-randomize, you get another design, and you do the test, and maybe you are close to the error rate. But the theoretical guarantee for a randomization test to be exact only holds on average across different experiments. So you imagine I have done this experiment with this trial sequence. I could have done it with another trial sequence. And on average, across all these, in a way, possible worlds, the randomization test would be exact, but not necessarily for your specific design. This problem with exchangeability in fMRI time series is a reason it might be smart to use means across trials or maybe GLM parameter estimates and apply the permutations to them, because we have the serial correlations in the time series. But if you have these, we have these means, and we have two different values, and of course they are still correlated. There are still error correlations between them, but these are the only two values that are correlated. So if we exchange them, we get exactly the same correlation structure. So on this level, exchangeability is again warranted. And if you do this with multiple runs, you get multiple parameter exchanges that you combine, and you get many permutations. So it might be, if you deal with fMRI time series, that run-wise classification is from an inference perspective, the better alternative. Not necessarily from a performance perspective, of course. I now quickly touch upon a related subject, how to deal with multiple comparisons. Of course, you can use the p-values you get out of a permutation test and apply some of the usual procedures, like Bonferroni correction for family-wise error or FDR or whatever. Fortunately, in permutation testing, there's a very nice built-in way to control for family-wise error. The precise correction, the degree to which you would have to correct your p-values, depends on the dependency structure between your different tests. For instance, you have a searchlight analysis or an ROI analysis. You assume some correlation between the tests in these different ROIs. Correcting for the number of ROIs or correcting for the number of searchlights is probably too much. It's probably conservative. But you can preserve the dependency structure in the permutation. And you do this by applying the same permutation across all tests. So you compute, you first have the data as they are, you compute the test statistic in each area or in each searchlight. Then you apply one permutation, and you compute the test statistic in your different searchlights or ROIs, and another permutation, and so on. So you keep the permutation constant across tests. You bind them together. What you get out of this is you have a test statistic array, Tij, where the one index I from 1 to np is a number of permutations, which are always the same across the tests, which are j equals 1 to nt, the number of tests. And then if you want to test the omnibus null hypothesis, is there an effect anywhere? Is the null hypothesis wrong anywhere? You can do this using the maximum statistic. You compute the maximum of the test statistic across tests, but separately for each permutation. And then you compare this maximum value with its own permutation distribution in the same way as before. Or you want to test whether there is an effect at a specific place, in a specific test, and you do this by, again, computing a p-value for this, but in this case, you're comparing the actual value in this place not with its own permutation distribution in this place, but with the maximum distribution. This way, you have a guarantee that the family-wise error is corrected. There are some extensions of permutation tests which are not exchangeability, not permutation proper. Sign flipping is one that can be very useful. Here the assumption is that you have a symmetric distribution. Here I have pictures of a univariate symmetric distribution, but the same idea of symmetry can also apply in the multivariate case. If you have the null hypothesis that the distribution of something is symmetric around 0, then you can, in a way, exchange the value with its negative. We could call this a sign flip test. And again, if we have the a violation of the null hypothesis that this is symmetric around 0, maybe it's still symmetric, but it's symmetric around something else. If you exchange x with minus x, you get a different distribution, so you do not have exchangeability, and this can help to distinguish between symmetry around 0 and not symmetry around 0. And another interesting extension, which is, I think, almost not used so far, is the idea of sphericity. In this case, you do not permute values, but you rotate them. The idea is that the joint distribution of values might be spherical, so the contour lines of this distribution are circles, or in higher dimensions, hyperspheres. So they are invariant under rotations if the mean is 0, but they are not invariant under rotations if the mean is not 0. And you can use this again to, for instance, test for a mean of 0 in a high-dimensional setting. If you're interested in this, come to my poster 1828 on Monday, please. Okay, here's a summary of some further reading about permutation tests in general. There are some nice introductory books, but if you really want to understand the theory underlying permutation tests, I can only recommend Lehmann and Romano. They have a very nice presentation, testing statistical hypotheses. There have, of course, been plenty of publications in neuroimaging, starting from the classic by Nichols and Holmes until the recent publications of Winkler et al. About different permutation schemes. There are also lots of publications on permutation testing in MVPA. Here I have to say a word of caution. I think that not all the authors here are completely clear on which null hypotheses they test and how exactly exchangeability applies in this specific case. And if you're interested in this variant, which is not a permutation test, but can be very flexible if you have randomized designs or randomized allocations, for instance, of treatments to patients, you can look into randomization tests. Again, a good theoretical source is Lehmann and Romano, testing statistical hypotheses. And if you want to have the company line on randomization tests, you should look into Edgington and Ogena. They think it's a solution to everything. Yeah, thank you very much. Any questions?
One quick question, because we're running late, and I don't know about you, but I don't want to miss the coffee break.
Hi. Thank you for this primer. One aspect that I have been wondering myself for a bit is using permutation tests for multiple comparison correction.
Mm-hmm.
Now, if my understanding is correct, we are assuming exchangeability of voxels there. And we have a situation in lesion to symptom mapping where the power, statistical power varies.
Okay.
And the same, I have been thinking, may happen to fMRI data, right? The bolt can be higher in one region and lower in another region and something like that.
Yeah.
So what do you think of that?
Yeah, you're absolutely right. Well, the way to correct for multiple testing is still correct. It doesn't matter how the null distributions vary over space. What you will get is you will get higher sensitivity in some areas and lower sensitivity in other areas. They are completely correct. So this only really works well if you can make some kind of homogeneity assumption across the different test statistics in the different locations. And the best thing I can recommend there is to look at your test statistic. I mean, something like classification accuracy has some built-in normalization, but still its distribution, especially in resulting from cross-validation, depends on many things. So maybe there's some way to tweak this to make it more uniform. Maybe you can have some kind of estimate of the null variance and therefore adjust the level in some areas, make it the level nicer in some areas and make them lower in other areas. So you have a tweaked version of the maximum statistics. This is the kind of stuff I would recommend.
But the correlation in a smooth fMRI data set, the correlation between neighboring voxels is not much of a problem in itself, right?
No. That's exactly this kind of correlation that is preserved if you use the same permutation across all test statistics. And that's why it is a precise correction for multiple testing.